Well, good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or stations further east. And a very warm welcome to you all on what for me has been a lovely sunny spring day. It's not quite spring yet, that's a couple of days' time, but it's been a lovely day and I've been out in the garden most of it. Thank you for joining this, the 39th of our regular series of short courses on pumping topics. This one will last 35 to 40 minutes, allowing us time for a Q&A session after the presentation. Well, here is a listing of all the previous short courses we've run during the last year. If you have missed any of them, you can get a copy of the materials from our website. Go to ruhrpumpen.com and follow the link to RP short courses. When you go to rp.com, here is the link to RP short courses. You click on that and it takes you to this page. You'll see all of the recent courses listed. Here are the latest 4, and you can click on any of them to download copies for your viewing at your leisure. Well, this is what we're covering today, the beginner's guide to positive displacement pumps, with a particular focus on reciprocating plunger pumps, which is the type that Ruhrpumpen manufactures. Now, a 1-hour session is certainly not going to turn you into a product expert, especially as I'm not an expert myself in this product line, but it will set you off in the right direction and give you a basic understanding. We will be holding a Q&A session at the end, so please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I will address those that I can live at the end of the session, and the rest will address by mail in the coming days. We're recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. Well, here is a summary of what we'll cover in today's session. We'll compare positive displacement pumps against centrifugal pumps. We'll answer the question, what is a reciprocating pump? And then we'll move on. We'll look at the Ruhrpumpen RDP pump, and then on to testing and the various package options. So first of all, how a positive displacement pump compares with and differs from a centrifugal pump. Well, with a centrifugal pump, energy is transferred directly to the liquid, which reacts by moving. With a positive displacement pump, you're moving the entire liquid boundary from A to B. So it's like this. Energy in, the fluid comes in and is sent out of the discharge. But the energy input is direct to the liquid. Whereas with the PD pump, it's the boundary of the liquid that moves. And the flow is the swept volume of the cylinder times the number of plungers. With a centrif pump, we have a pump curve, and the flow varies according to the system head. So as we close the discharge valve, we get a family of system curves, and the flow rate is determined where the system head curve and the pump curve cross. So here, here, and here. With a PD pump, the curve is vertical, or very nearly vertical. There is a small amount of compression. So the flow is constant, whatever the system pressure. So we end up with operating points here, here, and here. The maximum possible head with a centrif pump is the closed valve head. Now, the closed valve head with a PD pump is infinite in theory, but in practice, it's whatever the weakest link in the discharge side piping is. So without a relief valve, it will go up forever. The head increase is unlimited, a theoretically infinite head at closed valve, or until failure of the weakest part of the system. Bang. Or put another way, like this. Which is why you always have a pressure safety valve in the system, set to open well before you get to this point. The output of a centrifugal pump varies with speed or impeller diameter according to the affinity laws. So you get performance curves like this. The output flow of a PD pump varies directly with the speed or plunger diameter and stroke. So the faster the pump runs, the more is its flow rate. But how fast can a reciprocating pump actually run? Well, this is restricted by API 674. The standard says the max allowable speed has to be decreased for longer strokes, like this. So here's an example with a 50 millimeter stroke. The maximum speed is 450 RPM. And conversely, with a 200 millimeter stroke, the maximum speed is 210 RPM. The efficiency of a PD pump is much higher than a centrif pump and can be as high as 98%, although API 674 restricts this to 95% for calculating power. Well, there's the losses, and 95% goes as net flow. The power equals the pressure in bar times flow in litres per minute divided by 540. So that's how we calculate the power, which leads to the question, how is the motor sized? Well, API 674 says that the motor shall be sized in order to be at least 110% of the greatest power required for any of the specified operating conditions, including gear and coupling losses. So normally, practically speaking, it will be 110% of the pump absorbed power at rated flow and at the relief valve set pressure. Unlike with centrifugal pumps, with PD pumps, we have two commonly used terms for NPSH. We have net positive suction head available, which is the same as we have with centrifugal pumps, and we have NPIP, net positive inlet pressure. These are the same thing. NPIP is in terms of pressure, and NPSH is in terms of head. And normally either will be seen on a API 674 data sheet. It's the same principle as with a centrifugal pump. You have to provide a high enough pressure when the liquid is accelerated to avoid cavitation. So specifically for a reciprocating pump, the NPSH available has to provide force needed to open the valves and adequately fill the cylinders. The acceptance criterion is 3% flow drop rather than 3% head drop in a centrifugal pump. Remember, a PD pump is a constant flow pump. And as with API 610 for centrifugal pumps, API 674 says that the NPSH margin shall be a minimum of 1 meter. And the results of Lower margin than this, you'll have erratic and unreliable performance. You might get reduced flow in extreme cases and erosion of plungers and valves due to cavitation. Here we see it graphically. We've got rated flow up the side here, and we have NPSH available along the bottom. So we reduce the suction pressure, reducing the NPSH available, and we see that the flow stays constant, which is what we expect, until we get to a point where it starts to drop off. And when it reaches a 3% drop off in flow, that's the NPSH required for that pump. Now, this slide is an interesting concept for a centrifugal pump guy to comprehend. We're used to the idea that power is affected by SG. So if you're lifting something heavy, it uses more muscle. So high SG means higher power. But a reciprocating pump is not affected by SG. The analogy we use is that pushing a cubic meter of feathers and a cubic meter of lead from one point to another on a frictionless surface uses the same energy. And just to remind you, that energy, the power, is pressure in bar times the flow in liters per minute divided by 540. No mention of SG. Similarly with viscosity. PD pumps are largely unaffected by viscosity. So here we see increasing viscosity, and it's effectively a flat line. There's flow on this side. Effectively a flat line, it's constant. Whereas centrifugal pumps are significantly impacted. Flow, head, and efficiency fall significantly with increasing viscosity. So here are the key points to remember for a person who's coming across positive displacement pumps for the first time. The flow rate is determined by the pump. Suction and discharge pressure are determined by the system. The discharge pressure is only limited by the power supplied by the pump and the structural limits of the weakest component. A plunger pump does not create pressure. The system generates the pressure, and the pump pumps against this pressure. So, what is a reciprocating pump? It's a pump that moves a known quantity of fluid with each stroke of a plunger. Here's an animation to show you how it works. So there's the drive shaft. Here are the plungers. So there's the crankshaft here. There's the piston plungers moving through the packing here. Valves, inlet and outlet. So it comes in here and out there. So the Ruhrpumpen RDP pump is a reciprocating plunger type pump. So it's a plunger pump. It is a power pump. It is single acting, and it's a horizontal layout. We'll go into each of these four in a little more detail in the next slide. So it's single acting, which means it only works on the forward stroke, not in both directions. So it's not like this one, which this is a double acting pump working on in both directions. The RDP is a single acting pump. It needs mechanical input. It's a power pump. It needs a mechanical input from a motor or other motive power. It's not a direct acting pump like this steam-driven pump here. Now here we see the difference between a plunger pump and a piston pump. With a plunger pump, the smooth plunger moves through the packing, which are fixed in the stuffing box. It's good for higher pressure, lower flows. With a piston pump, the sealing elements move with the piston. It's good for higher volume, lower pressure. Reciprocating pumps can be manufactured in several configurations depending on the number of plungers. The most popular nowadays are triplex, quintuplex, and septuplex, having 3, 5, and 7 plungers. And here's why. Unlike centrifugal pumps, the flow rate of a recip pump is not actually constant. You are going to get pulsations. By the very nature of a reciprocating pump. The form of the pulsations depend on the number of plungers. Simplex being the most extreme, and quintuplex, here in green, being the smoothest, and septuplex even more so. We'll look in a little more detail at the Ruhrpumpen RDP pump. A sectional view of one there. Here is the RDP product range and the nomenclature for the pumps. As you can see, it's defined by the frame size, that is the plunger stroke, 100 millimeters in this example, and the plunger size, the diameter, 55 millimeters in this instance. Here is the range chart, and we see 7 sizes, with flows from as high as 3,000 liters per minute and pressures to 1100 bar. Here are the 7 sizes. Where there's a Q there, it indicates that it's a quintuplex pump, i.e. with 5 plungers. The others are with 3, they're triplex pumps. Pump selection is a balancing act between speed, plunger diameter, and rod load. So here, for example, a 200 millimeter plunger at 47 bar gives you a 1500 kilogram rod load, force being pressure times area. But so too does a 43 millimeter diameter plunger at 1000 bar. So our application engineers, when they're selecting the pump for you, they optimize the diameter and speed to give you the required flow for the system pressure while staying within the maximum rod load and give you the most economic selection. It's a juggling act. Here's an exploded view. We'll look at, in the following slides, at some of the major components. The fluid casing, the plungers, the stuffing boxes, the distance pieces, the crankshaft, the conrods, and conrods. Crossheads is what I meant to say, and conrods. In the coming slides, we'll look at those in more detail. So this is the power end or crankcase. This here is a power takeoff to drive force feed lubrication. The motor drive is at this end. Here's the power end again, and here is the distance piece box. Now this allows you to take out the stuffing box here for routine maintenance without disturbing either the power end or the fluid end. It also allows you to collect any leakage coming out of the stuffing box. This can be drained through this drain connection. It's an ambidextrous pump. It can be right-handed or left-handed. Here we show an option that is oil flood lubricated, but it can also be, and frequently is, a force feed lube driven. And here off this auxiliary power takeoff is the pump to circulate the lubrication, the oil. Moving on, this is the liquid end or the fluid head, which is available in varying materials and pressure designs. It's in cast construction for the high capacity and high pressure versions, and it has a forging for the very high pressure version with considerable worth 1100 bar. Here is the flow path through the VHP version. The flow comes in here into the suction. Here's the suction valve. Here's the discharge valve. And here it comes out of the discharge. Here we're looking at the valves. This is the Ruhrpumpen high performance valve, which exceeds the requirements of API 674. So it's a top guided bevel, high stability for greater efficiency, lower noise, with tapered seats for corrosion and erosion resistance. Now we move on to the plunger sealing assembly, the stuffing box. There are various options we'll choose from, depending on the surface and the pressures. Here is the stuffing box. Here's the plunger. Here is the gland nut, which compresses the packing, which might be braided packing or chevron type. And it might have a flushing or force feed system, depending on the service. This slide shows here the 5-ring braided compression packing. So 3 PTFE and graphite braided rings, 1, 2, 3. 2 PTFE and graphite and aramid braided rings. 6 anti-extrusion rings. It's simple and effective, but it requires regular manual adjustment by tightening this gland nut. There's the other common type, chevron ring packing. So multiple packing rings. It doesn't need anti-extrusion rings. Little adjustment is required, has fewer parts. And this is the spring-loaded packing for self-adjustment of the packing. So this spring allows for the relaxation of the rings, so you don't need to turn the gland nut. This spring compensates for the wear. There are various product lubrication, flushing, and force feed options that we'd select on depending on the service. Product lubrication is the simplest. There's no external flush. The pumped product migrates along the packing, cooling and lubricating as it goes. With flushing, typically shop or grey water under mains pressure or pumped pressure to provide cooling, flushing of the particulates, or prevention of crystallization. Third type and fourth type, forced feed. Used when you have low lubricity fluids, such as methanol, or for emission control, such as a closed drains pump containing H2S. A compatible fluid is pumped by an auxiliary pump driven by the power takeoff shaft extending from the pump crankshaft. You might have one or two feeds, a low pressure feed and a high pressure feed. Here are some typical system schematics. Here on the left, a low pressure system, giving a low pressure feed to each of the three stuffing boxes, this being a triplex pump. So there's 1, 2, 3, and you might have condition monitoring. Here on the right, a low pressure feed and a high pressure feed to each of the stuffing box on a high pressure application. So here's the low pressure feed, goes into the process side, and here the high pressure feed to the atmospheric side. And again, with some condition monitoring. Moving the state of the art ever onwards, the sealed rod box, zero emissions, gas tight, sealed distance piece chamber. When do you use it? Well, it's in addition to stuffing box sealing systems to prevent uncontrolled release of toxic or hazardous gases contained in the pumped media, such as H2S in the previous example. How does it work? Well, this distance piece chamber is sealed. You have gas-tight connecting rods with bellows seals. You have a nitrogen purge. There's a nitrogen input and out. The rod box is vented via a pressure relief valve, and any leakage is collected and pumped to a closed drain vessel. I'm not going to go through these next two slides in detail, but they describe the various stuffing box flushing configurations that are most commonly used, when you use them, and details of the construction and how they work. Also, as most of us here today are centrifugal pump guys at heart, and we're used to seal flushing plans, we tell you what the similar API 682 flush would be when there is one. So here's the first of the two slides. And here's the second slide. You'll get the hard copy of this and you'll be able to take your time and read it in detail. I'm not going to leave it up on the screen. So a bit of blatant product placement here. This is why we believe our pump is better than all the others. Just the one slide. I don't like to overdo the product placement in these. It's supposed to be an educational presentation. So we'll move swiftly on to testing. We do all the normal non-destructive testing, hydro, mechanical running, performance, noise, and NPSH. So hydrostatic testing, 1.5 times the maximum pressure for 30 minutes for API 674. The performance test, run at rated pressure and flow, and here are the API tolerances, +3%, -0% on capacity, and rated power, +4% tolerance. We frequently carry out a 4-hour running test. Now, per API 674, it has to be performed if specified, but something like 99% of customers require this test, as it's important to check the good performance of the mechanical parts of the pump, the power end, the gearbox, as well as the liquid end, the actual performance of the pump. We'll carry out an NPIP test or an NPSH test. The NPIP test, we take a trace, a plot of the inlet pressure made just upstream of any device used to improve the inlet flow, and compare it with the vapor pressure of the pumped liquid at the maximum allowable temperature. The NPIP test result shall be considered acceptable if there are no pressure spikes with peaks, no pressure with a peak instantaneous value greater than 3 times the mean inlet pressure, or a minimum value less than 110% of the above vapor pressure. Alternative is an NPSH test, where we reduce the system NPSHA, in other words, reduce the suction pressure until we get a 3% drop in flow, and that defines the NPSH required of the pump. Here is a short video of a pump on performance test. You can see the distance pieces here and the gland nuts. And here, the lubrication, the force feed lubrication to the seal chambers, to the stuffing boxes. And again, the lubrication to the stuffing boxes. And here, the sophisticated vibration monitoring system. If the pennies fall over, it's vibrating too much. Obviously, I'm joking here, but it is pretty smooth running, as you can see. So moving on, package options and auxiliaries, the last section of this presentation. These are the usual options that customers choose from. But basically, we make engineered packages. We give you what you want. Here are some typical examples in the following slides. Belt drive, either in the vertical or horizontal mounting. Gearbox drive, either with a foot-mounted motor or with a flange-mounted motor. Vertical drive through a right-angle gearbox if you've got limited ground area. And here with a booster pump on the same skid. This would be if you've got insufficient NPSH available for the RDP pump, you might fit a centrifugal pump as a booster, an NPSH booster, to provide flow into the suction of the RDP pump. Here, a force feed oil console. And here again, a force feed lube oil console, and also a canopy over the motor. And here are the auxiliaries we sometimes supply. First, pressure safety valves. You remember this slide? Bang. You must always have a pressure safety valve in the system. Here are the requirements. Now, either you can supply it or we can supply it. It's an option. The other auxiliary we frequently get involved in is pulsation control. You remember this slide from earlier? You are going to get pulsations. And you might want to dampen these pulsations for various reasons. Well, that's when you would need some form of pulsation dampening, which you can have the inexpensive bladder type, or the more expensive but maintenance-free acoustic type, where the flow takes a tortuous path through the dampener and prevents the pressure waves from traversing through the system. The pulsation limits might be set by the general rules of API 674, or by acoustical simulation, or by some other customer specified limit. Here's a typical layout, system layout, supply tank to suction filter. I'll come back to that. The suction dampener, there's the pump, the discharge dampener, and the discharge line, with a bypass line, minimum flow bypass line, back to the supply tank, and here the pressure safety valve, again back to the supply tank, not back to the suction pipe as well. We don't want to short circuit the pump. So, as I said, just a word on suction strainers. Generally, we don't recommend them. They reduce the NPSH and could block, causing cavitation and dry running, but it might be necessary to protect the pump from excessive solid content, in which case choose the coarsest mesh viable, and ideally use a duplex switchover type strainer with a differential pressure gauge on it. Well, that pretty much concludes the fun for today. I hope you found it useful. I just get to advertise the next of the short courses. Well, the next one is on vertical pumps, VS1, VS4, VS6. It's an updated version of one of our most popular sessions from January 2022, so 3 years ago. It won't be until the 24th of April, I'm afraid, as I'm away on holiday for most of March. The joys of being semi-retired. So that's 8 weeks away, 2 months away, 2 sessions, one for the Western Hemisphere, Eastern Hemisphere, and one for the Western Hemisphere. You'll get a reminder nearer the time. So I'm going to leave the meeting open for a little while to allow you to post in the Q&A box. And, well, I have to admit, I'm not likely to be able to answer many of the questions that you ask. But ask the questions anyway. I will send them to our product experts and we'll get you a written response. And anything you can think of later, email it to marketing@ruhrpumpen.com or to me directly, smith@ruhrpumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them, which won't be me. And they will be sending you the YouTube recording and a PDF of the presentation and of the summarized Q&A from both of today's sessions. If you need a certificate of completion for this short course, again, marketing@ruhrpumpen.com. And here, right at the end, are 8 slides about Ruhrpumpen to remind you of who we are and what we do. They'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. So I'll stop the screen share and let's see if we have any questions. It looks like we have 8 so far. I do have to say, I'm not a product expert. Any questions that are quite detailed, I'll have to pass on to our product experts and we'll get the answers to you in the next few days. Gerard Nagel says, can you go back over the power requirements? Isn't pressure dependent on the fluid density, which is related to the specific gravity? Yes, but the power calculation is based on pressure. So it's pressure times the flow times divided by 541. Uri Para says, do positive displacement pumps use a mechanical seal? No, they don't. They use packing. The different types of packing that I showed you in one of the slides, with, as necessary, some sort of flush to lubricate it and keep out the any rogue emissions. Gerard Nagel says, for the HP and LP seal fluid to the packing, why is the HP not on the process side where the pressure is highest, rather than the LP seal fluid as in the diagram? I'll get a proper answer for that one, Gerard. Sheldon Solomon says, which test is recommended, NPIP or NPSH? Either. Anonymous attendee has said, what is the acceleration head in this kind of pump? Again, I'll need expert answer for that one. Anonymous attendee again, for RDP pumps, do you usually supply protection due to forced lube oil pump failure? Example, a pressure switch that would stop the RDP pump? Yes, that could easily be built into the system, yes. Anthony Farrell says, how can you change packing by opening the distance piece without pulling the pistons or plungers? Are all packing elements split? Yes, if you go back and look at the sectional drawing, you'll see that it can just be lifted out. I'm not going to open up the presentation again, but what I'll do is when we get you the answer to this question, Anthony, I'll put in an exploded view that will show quite how that happens. Daniel Johnson says, are there any other instances where a PD pump is preferred over centrifugal pump besides when precise constant flow rate is required? Well, it's largely pressure as well. That's a thing. You know, these go up to 1100 bar. A centrifugal pump doesn't really go up that high. Samir Furfire says, can you list a few PD pumps pros over the centrifugal pumps in hydrocarbon pipelines? Can they be used as boosters for centrifugal mainline pumps? Well, yes. Whenever you've got high pressure, usually at lower flows, that's when PD pumps come into their own. Anonymous attendee says, many thanks, Simon. Fabulous as always. I assume you're referring to my waistcoat and tie. Thank you. Rouvier Davis says, What is the typical rotational design speed of the crankshaft? Well, the speed will depend on the stroke, and as you sort of seen in some of the slides, it can be 200 to 500 RPM. John Rogers says, will the slide deck be sent to us, or do we have to go to the website and download? You will be sent the slide presentation, a PDF version of this, but you can also download it if you wish. You can download them from all 39 sessions that we've had of these pumps, of these short courses. Daniel Holden says, we've always included a suction strainer as standard on our drawings. Is this not allowed? Well, it's certainly allowed. There is a risk if you have a suction strainer that it will clog, and that's what you've got to take into account. Our preference would be that you have a duplex strainer with a changeover, and use the coarsest mesh that you can. John Rogers says, you might mention that using a flow-through suction stabilizer will boost NPSHA by eliminating acceleration head loss. Thank you, John. Yamil Mina says, what is the recirculation line used for? It's a constant flow pump, remember? So if the system demand is for a lower flow, then the rest of the flow has to go somewhere, and that's where you'd have the bypass line. Yamil Mina says, what are the advantages and disadvantages of a bladder or acoustic type dampener? The bladder type is the less expensive option, but it has moving parts and it needs maintenance. The acoustic type is fit and forget, but it's a lot more expensive. Oliver Valadez says, we've manufactured some skids for, excuse me. We've manufactured some skids for oil and gas with PD pumps as redundant system, 2 in parallel, but only installed dampered pulsation at the discharge. We've not considered it at the suction line, only the Y strainer. Is that correct? I'll get an opinion on that from our product experts, if you'll allow. Yamil Mina says, Ruhrpumpen provides centrifugal booster pumps and positive displacement pumps in a single skid. Yep, we can certainly do that. Yes, and that was a simulation that we showed in one of the slides. Showed the two, but yes, that would be commonly what we would do. Are torsional analysis provided for larger PD pumps? Says Anthony Farrell. Yes, I believe so, but I'll get expert opinion on this. John Rogers has said, another tip, locate the pressure relief valve upstream of the flow through acoustic discharge dampener. That's the preferred method. Thank you, John. And he also says the pressure relief valve can be located downstream of an appendage gas charged discharge dampener. Thank you again, John. Yamil Mina says, is API 674's recommendation to maintain 10% above vapor pressure just a recommendation, or is it mandatory? Well, I think it would be, well, it's a recommendation. You can always take exception to what any of API 674's paragraphs if you wish. Wouldn't necessarily recommend it. Jorge Garcia says, what is the maximal operational temperature the pump can run at? I'll get you an answer. Osvaldo Greco says, does RP provide other type of PD pumps like screw, diaphragm, gear, etc.? Thank you for the presentation. No, this is the only type of positive displacement pump that we manufacture, which is why the presentation doesn't cover screw pumps, diaphragm pumps, gear pumps. So is that all the Q&As? We've had 25 questions. And I do apologize that I'm not an expert. I can't answer a lot of those questions, but I do have at my beck and call some product experts. I will send all your questions to them tonight, and within the next couple of days, we'll get considered answers to all these, and I will send that out to everybody who's asked a question, and everybody who's attended will get that summary as well in a few days' time. So, oh, here's another one. Do you offer cryogenic PD pumps skidded with insulation? Um, Another one that I'm going to need expert opinion on. You certainly do cryogenic centrifugal pumps. I don't know what our experience on cryogenic PD pumps is. So we'll call it a day there. It's 5 to 6 here in the UK, which means it's beer o'clock. I need to uncork one straight away. So thank you again for attending. I thoroughly enjoyed presenting it, preparing it, and I hope you found it useful. See you on the 24th of April for the next one on vertical pumps, about which I do know a lot, so you'd be okay for that one. Thanks a lot, guys. Bye-bye.